Now that we've discussed what a vector space is, I want to talk about a basis. The idea being vector spaces typically have an infinite number of vectors, and instead of dealing with each one of those infinite vectors, we tend to just use a basis, which most of the time is going to be a finite set of vectors that we can look at. A basis is going to be a set of linearly independent vectors that spans V. So I need to be able to write every vector as a linear combination of the basis, and it should be linearly independent. So the homogeneous system should only have one solution. The dimension of a vector space is going to be the number of vectors in that basis. So let's look at some examples. For R3, our standard basis is given by these vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. And this can be expanded to Rn as well. In general, we just want the columns of the n by n identity matrix for the standard basis. And I want to look at these three vectors, and I want to show that they are also a basis for R3. In order to do that, I'm going to put them in a matrix and row reduce. I need them to span and be linearly independent. When we start, we already have a 1 in the first row, first column. And I want zeros below it. We already have 1, so we just need to get this 0. And I'm going to do that by minus row 1 plus row 2. Minus 1 plus 1 is 0. Minus 1 plus 0 is minus 1. And 0 plus 1 is 1. Next, I don't need to get this in reduced row echelon form, just row echelon form. So I'm not going to worry about getting the zeros above, just below. So I'm going to add the second and third rows here. Minus 1 plus 1 is 0. And this is a 1, not a 0. 1 plus 1 is 2. And so now we can see that we have pivots in every column, which tells me no free variables, which tells me it is linearly independent. In addition, there's no row of zeros, so it does span. So yes, it is a basis of R3. In both of my last examples, I had two different bases for R3, but each of them had 3 vectors in them, which tells me that R3 is 3-dimensional. We also know that a subspace is also a vector space, so a subspace can also have a basis in dimension. So for R3, we have 4 different possibilities. We could be dimension 0, and this is just the origin, just a single point in 3-dimension space. We could have a subspace of dimension 1. This is a line through the origin. We could also have dimension 2, which graphically would be a plane through the origin. Miss my eye in there. Or we could have dimension 3, which would be all of R3. And we can't have a subspace with a higher dimension. So let's look at bases for subspaces. I'm going to let W be the span of V1 and V2, where V1 and V2 are these vectors here. Well, V1 and V2 definitely span W, since that's the definition of span and how I define this subspace. As far as linearly independent, with 2 vectors, if I can multiply one vector by a number and get the second vector, then they are dependent. And we can see that's impossible here. For one, it's impossible to multiply 0 by anything to get 2. So this is not true, which tells me that they are linearly independent. So this is a basis, in particular, a basis of dimension 2. Let W be the span of V1, V2, V3, where we know that 2V1 plus 3V2 minus V3 is equal to 0. I want to show that the span of V1, V2, V3 is the same as the span of V1, V2. There are essentially two things I need to show here. We're going to start by letting a vector u belong to, or be inside of, the span of V1, V2, V3. So I'm going to take a random element of this span of V1, V2, V3, and I need to show that it is inside of here, so that everything inside of this span is inside of the second one. The fact that W is in, or U is in here tells me I can write U as C1V1 plus C2V2 plus C3V3 by definition of U being in the span. Well, we can rewrite this slightly using this condition up here. So I'm going to take this condition and rewrite it as 2V1 plus 3V2 equal to V3 by just adding V3 to both sides. So then I'm going to write this as C3 times 2V1 plus 3V2. I'm going to rewrite again. C1 plus 2C3 V1 plus C2 plus 3C3 V3, or V2. And now I have this as a linear combination of V1 and V2. Since I was only able to write it as constant times V1 plus constant times V2, I can say that U is also in the span of V1 and V2. So that's the first piece. I need to do another piece as well. So that shows me that everything inside the first span is in the second, but I need to make sure the second doesn't have extra stuff. So I'm going to let W belong to the span of V1 and V2. And I need to show that it's also in the span of V1, V2, V3. So we know W is equal to A1, V1 plus A2, V2. And then I'm just going to rewrite this as A1, V1 plus A2, V2 plus 0, V3. So now I've written it as the sum of 3 vectors instead of just 2. And that tells me that W belongs to the span of V1, V2, V3. So I've now shown that these two are equal. And this is kind of a demonstration of my next theorem. The spanning set theorem tells me if V is a vector space with subspace W, which is the span of V1 through Vp, and if I know one of these vectors, let's say Vk, is a linear combination of the others, then the set formed by removing Vk still spans W. So if I know that one of them can be written as a linear combination of the others, I can ignore it completely and still have a set that spans. Let's look at an example using this. Here I have 3 vectors, and I want to find a basis and the dimension of the subspace of R3 that's spanned by these vectors. In order to do that, I'm going to start by putting them in a matrix. That's 1, 0, minus 3, 3, 1, minus 4, and minus 2, minus 1, 1. And then I'm going to row reduce. I already have my first 1, and I have a 0 below it. I just need to get the other 0 below it. I'm going to add 3 row 1 plus row 3. So that's 3 minus 3 is 0. 9 minus 4 is 5. And negative 6 plus 1 is negative 5. I'm now going to leave both the first and second rows alone and do minus 5 row 2 plus row 3. That'll give me a 0, 0, 0. So my actual basis, well, we can see that there's a pivot in the first column and the second, but not the third, which tells me for my basis, I'm just going to get rid of V3. My basis is V1 and V2 since that's where my pivots are. And that tells me I'm of dimension 2 since I have 2 vectors here.